Hi everyone, hope you're all doing well. Today I'll be beginning the video series for problems in the vector section of MCV4U. I'll be completing, I would say, most of the problems that Ms. Kranick assigns. When I say most, if there's, for example, right here in problem 1, there's H parts, I'm not going to do probably all of those. I think you'll probably start getting the idea around me doing like 4-ish maybe, and I'll leave the rest to you. Any of the more difficult problems, I will show solutions for here. So please leave a comment if you're unsure of what I did. But also remember that this should be done in tandem with you doing the homework yourself as well. As at the end of the day, math is a contact sport. You're not going to learn anything if you just watch me do it. It's good to try it yourself. Get a pencil and paper, maybe do it along with me if you'd like. All right, let's begin. So I'll also try for these problems explaining the background before I actually delve into the problems themselves. So for question 1, it's saying express each vector in terms of I and j. Well, that's pretty simple to understand, I would say. In the Cartesian plane, any vector, as a matter of fact, if you have some vector v, can be represented as a linear combination of unit vectors I. Oh, that's weird. Of unit vectors I and j. Okay, so that's what we're going to do. So let's begin. For 1, I'll do A. 2, 1. That can be expressed as 2i plus j. Make sure to add the vector symbols. Let's do D. 5, 0. That can be expressed as 5 lots of I plus nothing of j. Let's do G. I mean, actually, let's do F. F is 0, negative 8. So that would just be expressed as negative 8 lots of j. And H. Let's do H. Negative 5.2, negative 6.1. This would be expressed as negative 5.2 I minus 6.1 j. Okay. Pretty self-explanatory, I would say. All right, moving on. Let's do to question 2. This is just the reverse process. We now have a vector expressed in terms of the I and j unit vectors, and we want to express it in its more compact Cartesian form. So let's do A, I plus j. Well, that would just be the vector 1, 1. How about maybe F, 7i minus 4j. That would be the vector 7 minus 4. Let's do G, minus 8.2j. That would be the vector 0, negative 8.2. And let's do H, negative 2.5 I plus 3.3 j. Make sure to add your vector arrows on top. That's expressed as negative 2.5, 3.3. Nice. Okay, moving on to question 3. So the background needed for this, I would say, is we need to understand the ideas of position vectors. So as Ms. Kranick mentioned in the first unit, geometric vectors, vectors really don't care about their position in the Cartesian plane. They don't mind being anywhere. They could be out near the thousands, like quadrant 1, or they could be anywhere. It doesn't really matter. But it's convenient to have the tails of these vectors we're working with be at the origin. When we have the tails of vectors at the origin, we call them position vectors. Now, you might ask, why might it be useful to have the tails be at the origin in the first place? It's because of actually the thing I just erased, actually. It's easy to represent them in terms of the unit vectors I and j then. So that's the whole idea. So we're pretty much, for this question 3, we're pretty much going to be translating a lot of these vectors down to the origin, or the tails at the origin. So AB will go here, maybe somewhere, and, all the other ones in their respective positions. EF will go here, not to scale, obviously, but yeah, you get the idea. So let's begin. Oh, and that's erasing thing. Oh, never mind, perfect. Okay, so 3. So let's do AB first. How do we write vector AB as a Cartesian position vector? Okay, so we're pretty much going to subtract the coordinates we have at B from A. So let's subtract x values first. That's going to be 4 minus 2. 4 minus 2. And then we have, for the y values, 1 minus 6. Which is 2, negative 5. Moving on to CD. Okay, so for CD, same deal. We're going to subtract. We're always subtracting these ones from these ones. So we're subtracting the dx coordinates from the cx coordinates, and the dy coordinates from the cy coordinates. And that will be the case for all of them. So in this case, we have 0 minus negative 5. 0 minus negative 5, and we'll have 3 minus 2. Oh. And 3 minus 2. That leaves us with 5, 1. Okay. And the next guy, we have GH and EF. So GH. For GH. So same deal. This to this. And we have negative 4 minus negative 2. And the y values, we have 6 minus negative 3. So what does that give us? That gives us negative 2 and 9. And we have EF. I guess I screwed up the alphabetical order, but that doesn't really matter. So EF. The x coordinate matches, so we just have 6 minus 6, and we have 2 minus negative 5. And we're left with 0, 7. So that translates every vector now with its tail at the origin. All right, and let's close off this lecture with, or just, I guess you really can't call it a lecture, it's more me presenting the homework solutions. Let's close this off with doing question 4. All right, so A, B. And this is just using Pythagoras' theorem. Not too difficult. Make sure to put these single braces to indicate that we're taking a magnitude. That's important convention. And the last one, we have EF. Let's calculate all of these. 2 squared. Squared. 29 here. 25 plus 1 would be square root of 26. And we have 7 for this guy. And then we have plus 9 squared, square root of 85. Nice. Okay, we'll carry on with questions 5 through 8 next, and then we'll finish the remaining ones off later. Thanks, guys.